Welcome back to Talk Tensors. We dig into the latest machine learning research. And today we're looking at a paper with a really unique approach to simulating itinerant electron magnets.
Oh, that's a mouthful.
It is.
What are those?
Yeah.
What are those?
Well, imagine electrons in a material, but instead of being stuck to individual atoms, they're free to move around.
Like nomads.
Exactly.
Oh.
Like tiny little nomads. And this itinerant behavior makes it really hard to model their magnetic interactions.
Yeah, so you're not just trying to figure out where each electron is, you're also trying to figure out how they're moving and how they're influencing each other's magnetic moments, all while they're zipping around.
Right. And it's a computational nightmare.
It sounds like it.
Yeah, traditionally you'd have to solve a complex quantum mechanical problem at every single step of the simulation, which uses a ton of computing power, especially for large systems or when you want to simulate over long time scales.
So what's the solution? Is it machine learning? It is. The paper we're looking at today is called Machine Learning Force Field Approach for Itinerant Electron Magnets by Shang-Zong and his team. And they use machine learning to speed up these simulations.
Okay, so break it down for us. How are they actually using machine learning to solve this problem?
Well, they take inspiration from molecular dynamics, which also deals with complex interactions. They build a machine learning force field, which learns the relationship between an electron's spin, its local magnetic environment, and the forces acting on it. So once it's trained on enough data, it can predict those forces without having to solve the entire quantum mechanical equation each time.
So you're giving the simulation a shortcut. Instead of number crunching every tiny movement, it's using this learned model to guess where those electrons are going to go.
Exactly. And they went a step further and focused on a specific model called the SD model for these itinerant magnets, which is a really popular model in spintronics research. And it looks at the interactions between localized magnetic moments. Think of them like tiny magnets attached to atoms and those free-roaming conduction electrons.
So they have the model, they have this machine learning force field.
Yeah.
What do they actually do with it?
So they simulated 3 different types of magnetic order in a triangular lattice, which is a common structure in these materials. But their machine learning model needed a way to understand the complex magnetic environment.
It needs more than just knowing where those tiny magnets are.
Yeah, so they had to create a magnetic descriptor to translate the arrangement of spins into coordinates that the machine learning model can understand. It's basically like giving the model a language to talk about magnetism.
So they taught their model to recognize patterns in how these spins are arranged. What types of magnetic order did they simulate?
Well, the first one was the classic one, the 120-degree order, where the spins form a repeating 120-degree angle pattern. It's a great example of magnetic frustration, where the spins can't all align the way they want to.
That at 120 degrees, what's next?
Then they did the tetrahedral order, which is a little more complicated. The spins actually point towards the corners of a tetrahedron, a 3D shape. And this order comes from Fermi surface nesting and something called biquadratic interactions. But basically, it leads to something called chiral symmetry breaking.
Wait, hold on. Chiral symmetry breaking, what does that even mean?
Imagine this. In a material with chiral symmetry breaking, the electrons can only flow one way, like a one-way street for electrons.
Oh, wow. That's cool.
Yeah.
So 120-degree order, the tetrahedral order, and what was the grand finale?
The holy grail of spintronics, the skirmion crystal. Skirmions are these super stable swirls of magnetism that are really promising for data storage and information processing.
Did they create the skirmion crystal in their simulation?
Well, this is where it gets interesting. The skirmion crystal should be stable in theory, but their simulations often got stuck in these weird metastable states with stripes of skirmions and things called bimorons.
Bimorons? That sounds even cooler than skirmions.
I know, right?
Why are they getting stuck?
Well, the paper doesn't really say. But it opens up new research questions. And this is really where machine learning is so powerful. It allows us to simulate things at a large scale so we can see things that we might have missed otherwise.
Like a new microscope for magnetism.
Exactly.
I'm already fascinated. We're just getting started. But before we move on, why is all this so important? Why should we care about simulating these magnetic structures?
Because this research could change the way we design and control magnetic materials for spintronics. We could revolutionize things like data storage, information processing, all thanks to these magnetic textures.
Okay, I'm ready to go deeper. Let's talk about the history of magnetic simulations and how this paper fits in.
So for a long time, the main way to simulate magnetic materials was this technique called density functional theory, or DFT.
DFT.
Yeah, and it's a powerful way to calculate the electronic structure of materials from scratch.
From first principles.
Yeah, from first principles. But there's a catch. It's really computationally expensive.
Ah, so that's where the need for a shortcut comes in. DFT is just too slow for something as complex as these itinerant electron magnets, especially if we want to see how they evolve over time.
Exactly. And it's not just the speed. DFT can't always capture those subtle interactions that govern the behavior of these materials.
That's where models like the SD model come in. They give us a simplified picture, but it's still very insightful.
Right. The SD model focuses on the interactions between those localized magnetic moments and the free-roaming conduction electrons. It's like zooming in on the most relevant part of the picture so we can do larger simulations for longer timescales.
But even with a simplified model, we're still stuck with that computational bottleneck of having to solve a quantum mechanical problem at each step of the simulation.
Exactly. And that's where this paper comes in, using machine learning to get around that.
It's like they've connected the accuracy of physics-based models with the efficiency of machine learning. That's pretty impressive.
It is, and this work is part of a growing trend in materials science. More and more researchers are using machine learning to tackle these tough computational problems. It's becoming a powerful tool for discovering new materials and figuring out their properties.
So we've covered the history of the simulation techniques.
Yeah.
What about the history of these magnetic structures they're simulating, these skirmions, bimorons, all that? It seems like those are pretty recent discoveries.
You're right, the study of these exotic magnetic textures has really taken off in the last couple of decades, thanks to new experimental techniques and a better understanding of the theory behind them. Like, for example, skirmions, those tiny swirls of magnetism. They were only first observed experimentally about a decade ago.
What makes them so special? Why are physicists so excited about these skirmions?
Well, they have this unique combination of properties that makes them super promising for a bunch of different applications. First of all, they're super stable, like tiny magnetic tornadoes that hold their shape. Second, they're tiny, which means we could store a lot of information in a small space. And last but not least, they're really easy to move around, which means they could be really energy efficient.
So it's not just fundamental physics. There are real-world applications here.
Yeah.
We could revolutionize data storage computing,
Yeah.
even things like sensors and energy harvesting.
Exactly, and that's why this paper is so important. By figuring out a faster, more efficient way to simulate these materials, it opens up the possibility of designing them and optimizing them for specific applications. It's like giving engineers a new toolbox to create the next generation of spintronic devices.
Okay, so we've talked about the what and the why, but this is Talk Tensors, and we like to push things a little further. So let's move on to our novel notions segment, where we take the ideas for the paper and see where else they can go.
I love this part. So the paper used the SD model, which we know is a simplification of the complete quantum mechanical picture. What if we could go even further and create machine learning force fields for more complex models?
What kind of models are we talking about?
Well, one exciting possibility is incorporating something called spin orbit coupling into the model.
Spin orbit coupling. That sounds familiar, but refresh my memory.
Sure, it's a relativistic effect that basically couples the spin of an electron to its orbital motion. And it's responsible for a lot of interesting phenomena, like the anomalous Hall effect, which is related to that one-way street for electrons we talked about before.
Right. So how would adding spin orbit coupling change our simulations? Would they be even more accurate?
It would definitely add some complexity, but it could be a game changer. It would let us simulate even weirder magnetic textures and dynamic phenomena. We might be able to see how skirmions behave in materials with strong spin-orbit coupling, which could lead to completely new types of spintronic devices.
Okay, that's amazing. But wouldn't adding spin-orbit coupling make the simulations even more computationally intensive? Wasn't that the whole problem we started with?
That's a good point, and it's something researchers are working on right now. It's all about finding the balance between accuracy and efficiency. Maybe we can develop new machine learning methods that can handle the extra complexity without sacrificing speed. Or maybe we can simplify the models without losing too much accuracy.
So it's like a balancing act between capturing more of the real-world physics and keeping the simulations manageable. Sounds like there's a lot of work to be done here.
For sure. And another thing we could explore is going beyond the rigid lattice approximation that was used in this paper.
Rigid lattice approximation, what's that?
It means that the atoms in the material are fixed in place in the simulation. They don't move. But in the real world, atoms are always vibrating, especially at higher temperatures.
Oh, right. It's like they're assuming the atoms are frozen when they're actually jiggling around.
Exactly. And these vibrations can actually have a big impact on the magnetic properties of the material.
So what if we let the atoms move in the simulations? What would that allow us to do?
Well, it would definitely make things more complicated, but it would also let us study things like magnetostriction.
Magnetostriction, another new one for me. What is that?
It's basically how magnetic fields can change the shape of a material. Some materials expand or contract when you apply a magnetic field, and this effect can be pretty significant.
So these materials can actually change shape in response to magnetism. That's incredible. What kind of applications does that have?
Well, magnetostriction is super important in all sorts of things like sensors, actuators, energy harvesting devices. Imagine a material that can convert magnetic energy into motion. That's what we're talking about.
I see the potential here. By adding lattice vibrations to our simulations, we could design materials with specific magnetostrictive properties for all kinds of cool new applications.
Exactly. And who knows what other amazing discoveries are out there waiting for us as we keep pushing the limits of machine learning in material science. This is just the beginning of a whole new world of exploration.
I feel like I need to upgrade my computer just to think about all these possibilities. But before we get too far ahead of ourselves, let's bring it back to our listeners. What's the main takeaway from this deep dive into the world of machine learning and magnetic materials?
I think the big takeaway is that machine learning is completely changing how we understand and design these complex magnetic materials. When we combine physics-based models with the power of machine learning, we open up a whole new world of opportunities for spintronics and beyond.
That's something for everyone to think about. We've covered a lot of ground today, from the nitty-gritty details of magnetic descriptors to the mind-blowing potential of skirmions and bimorons. We even peeked into the future and talked about how adding spin-orbit coupling and lattice vibrations could lead to even more incredible discoveries.
It's a truly fascinating field, and it's moving so fast. Who knows what amazing breakthroughs we'll be talking about on Talk Tensors in the years to come.
If you're as intrigued as we are, we encourage you to check out the full paper and all the resources we'll link in the show notes. And as always, keep those brains buzzing, and we'll see you on the next episode of Talk Tensors.